Hello everyone. This 5-minute video introduces HIERAMP, Coarse-to-Fine Autoregressive Amplification for Generative Dataset Distillation, accepted to CVPR 2026. The key question is simple. Can we replace a large real training set with a compact synthetic one, while preserving recognition performance and reducing training cost? Dataset distillation aims to learn a small synthetic dataset that can stand in for the original real data. A good distilled set should train models efficiently, require much less storage, and still deliver comparable accuracy. HIERAMP approaches this by injecting class tokens at every generation scale, so that the model can first localize class-relevant regions, then amplify them in a hierarchical coarse-to-fine manner. Formally, we start from a large real dataset and synthesize a much smaller set. The distilled images are then used to train a downstream classifier. The goal is not only to make images that look plausible, but to make images that contain the right discriminative information for the classifier to learn effectively. Existing distillation methods often optimize images as a whole, either in pixel space or latent space. Optimization-based methods can be effective, but their images may lack visual fidelity. Recent generative methods improve realism, yet they do not fully exploit the hierarchical structure of images. As a result, fine object details and class-specific parts can be underrepresented. HIERAMP instead builds on visual autoregressive generation, which naturally proceeds from coarse layouts to finer details. The backbone idea is the visual autoregressive model, or VAR. Unlike a one-shot generator, VAR predicts images progressively across scales. Coarse scales capture global layout and object structure. Later scales add texture, parts, and local visual evidence. This matches how semantic concepts are organized. Object shape constrains parts, and parts constrain fine appearance. The motivation is practical. Training on a large dataset can take days, and model selection can require repeating that cost many times. We therefore want synthetic datasets that are compact, informative, and robust. The central challenge is to generate samples that preserve the most useful semantic evidence, while also generalizing beyond a narrow set of memorized visual patterns. HIERAMP addresses this challenge by identifying important semantic regions and refining them during generation. Instead of treating the whole image uniformly, the method amplifies object-related regions at the proper scale. Coarse amplification encourages meaningful layout and object coverage. Finer amplification helps sharpen discriminative details that are useful for recognition. The formal objective is to generate a compact synthetic set S from the real dataset D, with far fewer images per class. A classifier trained on S should achieve performance close to one trained on D. HIERAMP implements this within the VAR generation process by injecting class tokens, using their attention maps to guide scale-specific semantic amplification. The framework has two major components. First, object masks are obtained using grounding DO and SAM2, which provide class-relevant spatial guidance. Second, during VAR generation, HIERAMP amplifies the object regions indicated by the class token attention. The important point is that amplification is applied scale by scale, so the method can shape global structure, mid-level regions, and fine details separately. The qualitative results show the effect clearly. Compared with the baseline, HIERAMP produces samples with richer object details, more meaningful quantities, and stronger alignment between the intended class and the generated content. The attention heat maps also show improved object background dependence, suggesting that the method is not just adding texture, but improving the semantic organization of the image. On ImageNet 1K with 10 images per class, HIERAMP improves classification accuracy across multiple evaluation architectures. The table compares baselines and the proposed method under the same distilled data setting. The main takeaway is that hierarchical semantic amplification provides better synthetic training data without relying on an explicit global proximity optimization objective. The same trend appears on smaller scale CVPR benchmarks. HIERAMP delivers competitive or improved classification accuracy on CVPR 10 and CVPR 100 across different images per class settings and evaluation models. This indicates that the method is not limited to ImageNet scale data, but can also benefit standard small-scale distillation benchmarks. The effectiveness study highlights the computational overhead. Adding class token amplification to VAR keeps latency nearly unchanged and peak memory essentially stable. Compared with diffusion-based generation, the reported time per image is also lower. This makes HIERAMP practical for producing distilled datasets at scale. Finally, the analysis explains why the method works. Amplifying coarse and middle scales increases token diversity and coverage, which supports varied object layouts. At fine scales, amplification concentrates token usage, focusing capacity on object-related details. Together, these effects show that hierarchical semantics matter for dataset distillation. HIERAMP turns that insight into a simple, efficient generation strategy for compact yet effective synthetic datasets. Thank you for watching.